Have you ever really stopped to think about how an email finds you? I mean, really think about it? It's not magic, it's an incredible system called network addressing. Today, we're going to pull back the curtain and see exactly how the internet knows where to send every single packet of data. Let's get into it.
Right, let's just pause on that for a second. You hit send, and somehow that message weaves its way through a global spider web of cables and servers to land on one specific device out of billions. How in the world does that happen? Well, that's exactly what we're going to break down. At its very heart, network addressing is really just a system of unique labels. You can think of it as the universal language that every single connected device speaks. It's what makes sure that when you ask for a web page, it gets sent to your computer and not, the one next door. So here's the game plan for today. We're going to start with what I like to call the Internet's postal service. Then we'll look at the two different addresses every device has. After that, we'll dive into the public versus private worlds online, see how digital neighborhoods get organized, and finally, trace the path your data takes to find you. Okay, first up, the Internet's postal service. And probably the most important idea to get your head around right now is that every single one of your devices, your phone, your laptop, even your smart toaster, actually has two completely different addresses. And here's the best way to think about it. One address is like the permanent serial number that's physically stamped onto the device itself. It never ever changes. The other one, that's more like the mailing address of the house it's currently in. One tells you what the device is, and the other tells you where it is right now. So first, let's talk about the MAC address. That stands for Media Access Control. This is that permanent serial number. It's a unique 48-bit identifier that the manufacturer literally burns into the device's network card. It's fixed. And its main job is to identify a device on a local network. So think all the gadgets connected to your home Wi-Fi. And this is the other half of the duo, the IP, or Internet Protocol address. This is the mailing address. Now, unlike the permanent MAC address, this is a logical address. It gets assigned to your device when it joins a network, and it's what's used to send data across the huge global internet. And just like a mailing address, it can change. Most of us get a new, dynamic one pretty much every time we connect. Okay, so let's put it all together side by side. The MAC address is physical, it's permanent, and it's used by local hardware called switches for devices to talk in the same room, basically. The IP address, on the other hand, is logical, it's temporary, and it's used by routers to send your data all over the world. See? Two different addresses for two totally different jobs, but they work together perfectly. Now, while we're talking about IP addresses, you should know there are two main versions. We started with IPv4, which gives us about 4.3 billion addresses. Sounds like a lot, right? Well, we've basically run out, and that's exactly why IPv6 was created. It gives us a number of addresses so massive, it's kind of hard to even imagine. It is, without a doubt, the future of the internet. So, wait a minute. If we've run out of the old IPv4 addresses, how can every single phone, laptop, and smart TV in my house have one? Well, the short answer is they don't. And the solution is this really clever trick that separates the internet into a private world and a public one. Your home Wi-Fi is the perfect example of a private network. Inside this little digital bubble, your router hands out special, private IP addresses to all your stuff. These addresses aren't globally unique. In fact, your neighbor's laptop might have the exact same private IP as yours. And that's totally fine because they're never, ever seen by the public internet. So how do all of those devices with private addresses actually talk to the outside world? They do it through this brilliant process called network address translation, or NAT for short. Just think of your router as the friendly receptionist for your entire home network. It's the only device in your house with a real public IP address that the rest of the world can see. Here's how that works in practice. Your laptop, with its private IP, sends a request to the router. The router takes that request, erases the private IP, and puts its own public IP on it before sending it out to the internet. Then, when the website replies, the router gets the message, reverses the swap, and sends the data back to the right laptop. It's the ultimate gatekeeper, letting dozens of devices share just one public identity. So NAT is fantastic for conserving addresses at home, but what about huge organizations? A big company or university might have thousands of devices. To manage all that efficiently and securely, they break their giant networks down into smaller, much more organized digital neighborhoods. And this process is called subnetting. It's really just like taking a massive city and dividing it up into distinct neighborhoods with their own postal codes. it makes traffic flow way more efficiently. It boosts security by keeping different departments separate, and honestly, it just makes the whole thing so much easier to manage. Now, I'm sure you've probably seen something that looks like this tacked onto the end of an IP address before. A slash followed by a number. What on earth does that mean? It looks so simple, but it's an incredibly powerful little piece of information.
This is what's known as CIDR notation. And that /24, just think of it like the neighborhood's postal code. It tells any router that the first 24 bits or the first 3 numbers of the IP address identify the neighborhood, and only that last number identifies the specific house or device. It's just a super efficient shorthand for defining the size of a network.
All right, we've got our permanent serial numbers, the MAC addresses. We've got our temporary street addresses, the IP addresses. We have public and private worlds, and we have organized neighborhoods. Now for the final piece of the puzzle, how does a packet of data actually complete the last few steps of its journey? And that brings us to a really crucial question. Your router knows it needs to send some data to, say, 192.168.1.5. But remember, for that final delivery on the local network, it needs the physical MAC address. So how does it bridge that gap between the logical IP address and the actual physical hardware? Well, it uses something called the Address Resolution Protocol, or ARP. It's actually pretty brilliant and simple. The router basically just shouts out to everyone on the local network, "Hey, who here has this IP address?" The correct device hears that call and it replies, "Oh, that's me, and here's my permanent MAC address." Just like that, the router now knows exactly which physical device to send the packet to. So that covers the local delivery. But what about the long-haul journey across the internet? Well, that's the job of routers. They are the traffic police of the entire global network. At each step, a router looks at the destination IP address on a packet, checks its internal map, which is called a routing table, and then sends the packet one hop closer to its final destination. Your data might make a dozen of these hops to get across the world. And all of this brings us full circle. These clever systems like NAT and subnetting, they were mostly invented to deal with the problem you see right here. We have pretty much run out of IPv4 addresses. The future of a truly connected world with billions and billions more devices depends completely on making the move to the vast, almost limitless supply of IPv6. So really, the bottom line is this. Network addressing is the invisible backbone that makes our entire connected world possible. It seems complicated, but it's just the set of rules, the universal language, that lets all of our devices find and talk to each other, whether they're in the same room or on opposite sides of the planet. So, we solve the address shortage problem with IPv6, but that leaves us with one final big question to think about. As we connect trillions more devices and demand even faster and more secure communication, what's the next huge architectural challenge for the internet? What comes after addressing? Thanks for joining me for this one.